So a couple of announcements before we actually start. Like I said, we've modified the lab syllables. You guys will get more detail about the syllables during your lab hour. That's the first thing. Secondly, the class syllabus is also going to be modified because we need to accommodate this current situation. But the first thing I would like to let you know is that our exam that was scheduled for this Friday the 27th was moved to Friday the 3rd of April. So the exam will not be this week, but the following week. Okay, it will be an online exam. You guys will be required to take the exam at the same time. So it will either be during class time or at an odd hour of the day. We'll choose an odd hour where everybody is connected and we'll take the exam at that time. That's what we're going to do. Number of exams, we've reduced the number of exams from 5 exams to 4 exams. Okay. Normally you're supposed to have exam 3, 4, and 5, but now you will only have exam 3 and 4 left, plus your finals. And exam 4 is scheduled to take place on April 22nd. Exam 4 will take place on April 22nd, then the final will follow. That's a little bit of change we have on the syllabus. So once we put that on writing, we'll let you guys know about it. So this was just an information. Now, before we start today's class, I want to find out, is there any question or anything you guys want us to review before we continue?
The answer to the last question we did from last class.
Oh yeah, is that Reina Garcia?
Yes.
Okay. I'm trying to, because when I have my full screen, I can't see the names. Oh, the answer to the last question we did before we closed last class. Yes, let's continue from there. The answer to this question, right? And I guess we have reduced our choices to A, C, and E. Let's start it from the beginning. What we did was we decided to label this as carbon 1, carbon 2, carbon 3, and carbon 4, and label this as carbon A and that one carbon B. The first thing I said, we will notice why I decided to label this carbon A and then decided to label this carbon B instead of labeling this one A and the other one B. We'll look at it in details today. And we know that carbon 1 is always connected to carbon A and carbon 4 is always connected to carbon B. Because we have a 4 carbon versus a 2 carbon, we automatically know that we'll produce a 6-member ring. Does that make sense for everyone? You have 4 carbon and 2 carbons combining. So that gives you a total of 6 carbons. So you are forming a 6-member ring. And then 1 is always connected to A, 4 is always connected to B, and then you create a bond between 2 and 3. So that's what your general structure will be. And so those A, C, or E for now are correct. For now are correct. So let's continue today's class. We'll come back to this question. We'll come back to it after the first part of today's class. Any other question, guy? So let's look at it. So we said for the Jones-Elder reaction to be effective, your diene need to be locked in the S conformation. So when the diene is locked S conformation, you have high chances of undergoing your Jones-Elder reaction. And that's your dienophile over there. And so with your dienophile, in this case, this will be my carbon A and that's my carbon B. Okay, look at the way I draw the structure. This structure may look fancy. I know that carbon 1 is always connected to carbon A, and then carbon 4 is always connected to carbon B. Then I will create a double bond between 2 and 3. And so you can observe here the double bond between 2 and 3. And then you can easily refer to this as carbon A and refer to this guy as carbon B. Does that make sense? Then carbon 5, I want you to notice the behavior of carbon 5. Carbon 5 is connected between 1 and 4. So carbon 5, the way you could draw it was a little bit out of the structure. And so that will be our carbon 5 there between 1 and 4. This kind of molecule are referred to bridge bicyclic compound. We refer to them as bridge bicyclic compound. And you will notice that we have two types of product here. In this case, we'll be able to form two products. One product in which the carbonyl group is face downwards, meaning in the axial position technically, and another product in which the carbonyl group is pointing at the equatorial position and away from the ring. Does that make sense? Those are the two types of product we form. And so, like in chemistry, remember, we like to give names to things. We like to describe things by their name. We like to describe things by their name. And so, the one in which the carbonyl group is pointing downward, meaning this guy here, usually we refer to this as the endo product. Endo, meaning inside. Okay, that's the meaning, endo. And then this guy here will refer to it as the exo product, meaning outside, external to the ring. So exo, because it is the carbonyl group is pointing away from the ring. Does that make sense? So it's kind of like extending the ring. That's why we refer to that as the exo product. Okay. Okay. Does that make sense? So in this case, our endo product is the major product. Endo versus exo product. Endo versus exo product. First things are the endo product. The group or the substituent does not point away from the double bond. Okay, so this is the double bond of interest here. That's our double bond of interest. The substituent does not point from the double bond, but with the exo product, you notice that the substituent is far away from that double bond. That's the difference between an endo and the exo product. Now, the endo product is formed faster. What does that mean to you guys? I need someone to say.
More stable.
So I need another answer. Faster. What does faster mean?
It's the kinetic product.
Hallelujah. Gracias. Merci beaucoup. Thank you. Faster means is the kinetic product. Does that make sense, guys? So the endo product is formed faster. Remember, anything that has to do with speed is a kinetic product. The endo bond is formed faster. And so what will you say about the exo then? The exo will be which type of product?
Thermodynamic.
Thermodynamics. Okay, so thermodynamic has to do with stability. So the exo product usually is more stable than the endo product. And remember, I always said this in class. Stability does not mean major product. If you are stable, it does not necessarily mean you will be the major product. Okay, major or minor product depends on the reaction condition. That's what you need to keep in mind. Now, why does the endo product forms faster? That's the question. Why does the endo product form faster? If we compare the transition state, endo versus the transition state of the exo, this is just for your explanation, for appreciation. I don't expect you guys to draw this. I will never ask you to draw this thing. Okay. If you look at the transition state, you'll probably just notice that the way the arrangement is, depending on what this substituent is, you can easily have interaction between the R group and the double bond. And that interaction usually gives stability to the transition state. And remember, when the transition state is stable, the reaction goes faster. Okay, when the transition state is stable, the reaction goes faster. That's basically what I want you guys to appreciate. Now, in terms of the stereochemistry of the Giles-Elder reaction, this is the section of the class that will help us finish answering the question we started last time. In terms of the stereochemistry of the Giles-Elder reaction, now we have our diene. This is the diene because we have the double bond, and this portion of the molecule will be our dienophile, meaning the guy that loves the diene. That portion of the molecule will be the dienophile. Now, we have no idea. We have no idea of the stereochemistry of the dienophile in this case. Okay, you have no idea of the stereochemistry of the dienophile. So what I mean by that is that when you look at the dienophile, you cannot tell if the dienophile is a cis or a trans dienophile. And so because you cannot tell if the dienophile is cis or trans, you notice that you end up having a mixture in your product. You end up having a mixture in your product. You are creating a chiral center. Look at that. You have a chiral center over there. That's a chiral center. And whenever you have a chiral center, you should think of your R and S configuration. So one of these centers will be R, the other center will be S. I don't know which one is R, I don't know which one is, but I know one of them will be R, one of them will be S. And so you see, we end up having a mixture. We end up having a racemate. So when you are reacting to create new asymmetric center, chances are that you will end up having a racemate. Okay, but then you can control the stereochemistry of your reaction. You can control the stereochemistry of your reaction. Please take note. This is very important. And the stereochemistry of your product. So the stereochemistry of the product is a function. It's a function of the stereochemistry of the dienophile. Well, it's too much. It's too much to write. The stereochemistry of the product is a function of the stereochemistry of the dienophile. So what I mean is that the stereochemistry of the product determines the stereochemistry of your dienophile. So if you are starting, this is my diene. I want you to take note. That's the diene and that's the dienophile. So because we are starting with a cis dienophile, our products will be cis. Will form two types of product. Cis. A product in which both of them are in the dash or both of them are in the wedge. That's the meaning of cis. Take note, this is similar to drawing. I don't like the way they drew this molecule here. Sometimes it's a little bit confusing. Okay, this molecule here can also be drawn this way. You may decide to draw it this way. Does that make sense for everyone? So I'll call this molecule A, I will call that molecule A. So when you have a cis dienophile, you will produce two products, one of which the substituent will be on the dash, on the wedge, and then the other one in which the substituent will be on the dash. And so you can draw it the way I drew it, or you can draw it the way it is represented down there. So I will really advise you guys to draw it the way I drew it so that we avoid any confusion. Okay, we avoid any confusion. So that's the stereochemistry of the reaction. Stereochemistry of the reaction is a function of the dienophile. And so if we start with the trans dienophile, oops, guys, don't send what is it, chat message to me. I would rather prefer, yes, Christine, go ahead. If you have a question, because I am using a share screen, it's hard for me to see your hand. So if you have a question, just go ahead and just go ahead and ask the question. Okay, if you have a question, just go straight and ask the question.
Okay,
Yeah.
if so, you're saying all this, but like at the top of the screen it says if the reaction creates two new asymmetric centers. Does that happen often?
Yes. Well, most of the time, you will end up having two new That's if you have two new symmetric centers, that's the only time you can have a cis or trans. If your dienophile is cis or your dienophile is trans, you will always create two new centers.
Okay, thank you.
Yes, because I haven't seen a case where you don't. Does that make sense, guys? So that's what I want you to remember. So let's go back to the question. And from the question now, we can now eliminate some of the choices that we had at the beginning. Remember, we were limited. Our choices, we ended up having A, C, and E as choices. A, C, and E. So based on what we've done right now, let me make a poll so that we can continue from there. My first, how do you call it? My first attendance. So we have A, C, and E. So based on what we've done right now, what would be the answer between A, C, and E? Oh, let me see. Guys, remember that the poll is kind of obligatory, okay? You must answer the poll, but you must not necessarily have the correct answer. Does that make sense? You must answer the poll because I use that for my attendance, but you must not necessarily have the correct answer. But if you have the correct answer, I'll be so happy, you know.
Can you scroll up so we can see the rest of the question?
This way,
Yes, thank you.
I'm still waiting for 10 responses. We have 20 seconds left. 10 seconds left. Okay, great. So I guess the 7 people who didn't answer, they are probably sleeping. They probably logged in and then went back to bed. They think I don't know. So those are the responses. Those are the responses. Thank you for your responses. Now, let's start. The dienophile, Shelby. What's the stereochemistry of the dienophile? Is that a cis or a trans dienophile?
It's a trans.
It's a trans, okay? So our dienophile is trans. So what should we expect the product to be?
Trans.
Trans, okay? So when you look at A has no stereochemistry. So it can never be A. When I look at B and my stereochemistry at E, sorry. When I look at the stereochemistry at E, that's a cis stereochemistry. So E would not be the correct answer. And when I look at the stereochemistry of C, it is a trans stereochemistry. So the best choice to this question would be C. Thank you, Shelby, and thank you, Raina, for reminding us to get back to this question. Now, remember that I had to change the position of A and B in this question. Look at this question, the way I labeled it. The way I labeled the question, I decided to label this one A and label this one B instead of doing the opposite. And there was a particular reason for that. There was a particular reason for that, and I told you guys that I will come back to why I decided to label it that way. Okay. Uh, what is? We'll come back to that slide. Let's talk about. Oops, it looks like the slide is no longer there. Well, before we talk to this slide, let me explain why I decided to switch A and B. For the first case where I decided to switch A and B, if you look at my diagonal file this way, if you look at the way the diagonal file was drawn, that's how it was. And I decided to call this one A and call that one B. There was a particular reason. If we decide to draw the resonance structure of this compound, if we draw the resonance structure of this compound, this electron moves here and those electron moves over there. You will now have this as a resonance structure, and then there will be a positive charge here. Okay, there's a negative charge over there and a positive charge. So the carbon atom that ends up being positive in the resonance structure is the one that I always make A. In other words, the carbon atom that is far away from the carbonyl group is always my A. That's the way I always do to know, to keep in mind, to be able to know exactly how I need to draw my product. The carbon atom that is far away from the carbonyl group is always the A, because when I draw the resonance structure, that carbon atom ends up having a positive charge in my resonance structure. And having that positive charge, as you will see in the chemistry of benzene, will refer to it as being activated. Does that make sense? Okay. Now, coming back to class, what we have here is what we refer to as a retrosynthesis. We refer to this as retrosynthesis. So, retrosynthesis in the sense that I give you the product and I ask you to give me the starting material. So I can give you a product of a Giles-Eller reaction and I ask you to give me the starting material. And usually the best way to do that is to label, the way I always do. You remember, in this Giles-Eller reaction, the double bond is always formed between carbon 2 and carbon 3. That's why you know for the product of the Giles-Eller reaction. And you know that carbon 2 is always connected to carbon 1 and carbon 3 is always connected to carbon 4. As a rule of thumb in this class, I always told you that carbon 1 will be connected to carbon A and carbon 4 will be connected to carbon B. Does that make sense? So once you have that in mind, then you can draw your starting material. You now move backward. So backward in your starting material, this will be my 1, 2, 3, and 4. Then this will be A and B. And notice that my A and B are in the cis conformation. They're in the cis conformation because the proposed Giles-Elder product were both on the dashes. They were also cis. That's why over here, I am locked in the cis conformation. So that's what we refer to as retrosynthesis. That's the best way to know. Okay, that's the best way. And so with this, I would say we are done with the Giles-Elder reaction. Yes, Katie. Usually, if you have a question, Katie, just unlock your mic and then ask the question, because it's hard for me to see when you raise your hand when I'm using the full screen.
Right. Can you hear me?
Yes.
On the page above, I thought you said that the carbon atom furthest from the carbonyl is the A.
Oh, yes. Usually that's the way I do it. Yes, that's the way I usually do it. But in this situation, okay, maybe it's the way I do my labeling. Okay, let's do the labeling. If I have to do that, the labeling here, this will be my 1. Oh, sorry. And I will label it, this will be my 1, that will be my 2, 3, and 4. So that this now becomes carbon A and that one carbon B. Yes, thank you. That was a nice card. I think that's the best way to label it.
So it is then always A for the one furthest away?
Yes, A is always the one furthest away.
Okay, thank you.
Yes, A is always one furthest away. Thank you for the catch. Thank you. It means you all, I appreciate it. Thanks. So that said, we are done with the Giles-Elder reaction. That's basically what we are. We're done with it. So basically, to recall the Jones-Eller reaction, you know it's a reaction that it's a 4+2 reaction because you are using 4 pi electron from the diene and 2 pi electron from the dienophile. You end up forming a 6-member ring. You end up forming a 6-member ring for the Jones-Eller reaction. And in the Jones-Eller reaction, reaction, yes.
Please explain why you changed the labeling.
Say that again. Explain why.
Yeah.
No, I didn't get the question, Kara.
Can you explain why you changed the labeling from the B to A?
Oh, simply because we need to keep our convention that carbon A must always be the furthest carbon away from the carbonyl. So to keep the convention that carbon A must be the furthest away from the carbonyl, and that carbon A must be connected to carbon 1.
Got it.
Yeah, so as I recall, just earlier we form a 6-member ring. The stereochemistry of the product depends on the stereochemistry of the dienophile. So if you have a cis dienophile, your product is cis. If you have a trans dienophile, your product is trans. And then in terms of the diene, the S cis conformation is favored over the S trans conformation. If you have a molecule that is locked in the S trans conformation, there will be no reaction. But if the molecule is locked in the S cis conformation, the reaction is faster. In terms of the Jones-Eller reaction, an electron withdrawing group on the dienophile activates the reaction, increases the speed of the reaction. Those are the things we need to remember here. Now, we're looking at the last concept that I want us to talk about.
Dr. Zico?
Yes.
So for only in the Diels-Alder reaction, the A must be furthest away from the carbonyl?
Yes.
Okay.
So we're looking at the last concept of this chapter 8, then we'll move to chapter 18. So delocalization of electron makes a compound more stable. This is not news, right? We're kind of familiar with it. Delocalization technically is a cousin to resonance. So the more delocalization or the more resonance you have, the more stable the structure is. And here we have three different types of molecule. We have a cyclohexene molecule, meaning with one double bond. We have a cyclohexane molecule. And then we have another type of molecule, we refer to it as a benzene molecule. Okay. And if you notice, is that the more delocalized electrons you have, the more stable the molecule will be. Okay. The more delocalized electron you have, the more stable the electron will be. And so among this structure, let me see where it looks.
So, Dr. Zico, why is the first one cyclohexene less stable than the cyclohexane without no bond?
No, cyclohexene is more stable than cyclohexane.
Okay.
But here in this case, the comparison is a little bit misleading. I don't like the way this slide is because usually it's good to compare apples to apples, meaning that it's good to compare the ones that have the same number of carbons and the same number of hydrogens together. And so in this case, it will be easier to compare cyclohexatriene with localized electrons to benzene with delocalized electron. And if you see that if you need to do that comparison between cyclohexatriene that has a localized electron and benzene, you notice that benzene is more stable because it's lower in energy. And what makes benzene more stable are the delocalization of electron. Okay. So for me, the take-home message on this slide is that the more delocalized electron you have, the more stable your structure will be. Okay. More delocalized electron, the more stable your structure will be. And so benzene fall in a class of molecule referred to as aromatic compound. Refer to them as aromatic compound. And aromatic compound usually a stable molecule, and it will be a duty, it will be a tax. Benzene is not the only aromatic compound. There are several other types of aromatic compound. It is your duty and your task to be able to recognize if a molecule is aromatic, non-aromatic, or anti-aromatic. And that's what we have to do in this class. That's basically the purpose of this section, to be able to determine the aromaticity of a molecule. If a molecule is aromatic, okay, so we'll be looking at three types of stuff. If a molecule is aromatic, if the molecule is non-aromatic, or if the molecule is anti-aromatic. Those are the three things we have to do in this class. So in order to determine if a molecule is aromatic, first criteria, the molecule must be cyclic. So over here, when I see this by benzene, I see the molecule is cyclic. So that's the first criteria, cyclic molecule. Okay. Secondly, the molecule must be planar. What does that mean for a molecule to be planar, guys? Anyone? What does that mean for a molecule to be planar?
Is it trigonal planar, so sp2?
Hallelujah, gracias. Thank you very much. Okay. When we mean the molecule is planar, it means that all the carbon atoms in that molecule forming that cyclic system must be sp2 carbons. Or does that make sense? All the groups making that molecule, they must be sp2, all the carbons must be sp2. That's what it means to be planar in that case. I said all the carbons must be planar. Now the molecule must be fully conjugated. You know what it means by to be fully conjugated? Alternation of double and single bond. Double, single, double, single, double, single, double, single. And you can see that with the benzene molecule over here. I have a double, a single, a double, a single, a double, a single. So I have it fully conjugated. All the carbon atoms in this molecule here are sp2 hybridized. So that takes care of the planarity. The molecule must have an odd number of pi electron. Must have an odd number of pi electron of pairs. I will add the word pair. It should be a pair. So they must have an odd number of pi electron. So for example, in the benzene, this is a pair of pi electron. That is a pair of pi electron, and that is a pair of pi electron. And you notice that over there we have a total of 3 pairs of pi electron. Does that make sense? We have a total of 3 pairs of pi electron. So those are the 4 things we need to follow for a molecule to be aromatic. Does that make sense? Now, so for example, these are some examples of molecules that we'll see if they are aromatic or not. Let's follow the criteria for aromaticity here. Let's look at the first molecule, cyclobutadiene. Okay, let's look at cyclobutadiene. Rule number 1, the molecule is cyclic. The molecule is cyclic. Check. Rule number 2, the molecule is planar. Let's see. This carbon is sp2, this carbon is sp2, this carbon is sp2, this carbon is sp2. All the carbons are sp2. Check. Does that make sense? Rule number 3, the molecule is fully conjugated. Let's see. Double bond, single bond, double bond, single bond. Check. Does that make sense? Rule number 4. Rule number 4. What does it say? The molecule has an odd number of paired pi electron. Odd number of paired pi electron. So in terms of pi electron, I have 1 pair, I have 2 pair. So is that odd? 2 is not an odd number. So 2 is an even number. You fail. So that's why this molecule is non-aromatic. Does that make sense? That molecule is not aromatic. We can do the same thing with cyclooctatetratriene. Cyclooctatetratriene will pass the test of being cyclic. It will pass the test of having a planar structure because all the carbons are sp2. It will certainly pass the test of having alternating double and single bond, but it will fail the test of having odd number of pair electron because here we have a total of 4 and 4 is not an odd number. Does that make sense, guys? Now, non-aromatic compound. In this case, let's look at all of these case one by one, okay? If you look at the first molecule here, cyclopentadiene, let's look at cyclopentadiene again and double check and see all the problem. Yes, it is cyclic. Yes, I have an alternation, double, single, double. I have that alternation. But then, take note. How many pairs of pi electrons do I have here? 1, 2. So it failed the test of the number of pairs of pi electron. Is the molecule planar? No, the molecule is not planar because I have a sp3 carbon over there. So this guy failed 2 tests. So this is a non-aromatic molecule. Does that make sense? Now, next off is the cyclopentadiene cation that we are looking at. Yes, the molecule is cyclic. Remember, because we have the rules, cyclic, planar, conjugation, and odd number. Those are the rules, okay? Cyclic, planar, conjugation, odd number. So in terms of cyclopentadiene cation, it is cyclic, it is planar, okay? Planar because this is sp2, this is sp2, this guy also is sp2, sp2, sp2. So all the carbons are sp2, that's why it is planar, okay? Yes, it is conjugated. I have a double, single, double. But technically, it's not fully conjugated. Remember, they said fully conjugated, okay? But yes, it is conjugated. Now, in terms of odd number of electron pair, it doesn't have odd number of electron pair because I have 1 and I have 2. Does that make sense? So it fails the test. Now, next one, cyclopentadiene anion. Cyclopentadiene anion. It is cyclic. It is planar because all the carbon are sp2. It is conjugated. And it will have an odd number of electron pairs. Somebody should ask me a question. Why, right? I guess the question would be why. Why? Because of these electrons here. Those electrons are also pi electrons. Any question? Let me see. So does that make sense, guys? Those electrons are also pi electrons. This is a special case here, as you can see. These are pi electrons. And so cyclopentadienyl anion is aromatic. And it is a pi electron because this electron can actually take part in formation of a resonance structure. If you decide to draw the resonance structure of this, you can actually form a resonance that will go overall, that will go through the ring.
If it has resonance, wouldn't that mean it's not fully conjugated?
No, resonance actually means you're fully conjugated. That's what brings about full conjugation. And that's also why this guy, remember this one we said it passed the test of conjugation. And one of the reasons why it passed the test of conjugation is because you can do resonance on that molecule. Take note. Look, I can do my X, Y, and Z. Do you see that? And the star will be the positive charge. So because I can do my X, Y, and Z, means that one I can also do resonance. That's why it is fully conjugated. But it failed the test because of the odd number of pi electrons. Although it can do resonance, it only has an even number of pi electrons. This one here can also undergo resonance. It can also undergo resonance, X, Y, and Z. In this case, the star will be the lone pair of electrons. And so those lone pair of electrons are also pi electrons. So it contributes to the number of pair of pi electrons. That's why you have an odd number of pi electrons. And that's why this molecule is aromatic. Does that make sense? So your job in this section will be to determine if a molecule is aromatic or not. And so, like I said, cyclopentadiene anion, the anion can undergo resonance. And that's what this slide is showing here. This is my X, that's my Y, and that's my Z, and that's the star. And so you can undergo resonance and it will go all over, all over. Now, please, when I ask you to show resonance in the future, henceforth, I want to see your arrows. Don't just draw the structure to me. Show me the arrows. I want to see how the electrons are moving. For example, in this case, you see they have shown the arrow. Here, if I want to show, let me call this structure A, structure B, structure C, structure D. I want to see the arrow that makes you to move from structure A to structure B. And in this case, this is my X, that's my Y, and that's my Z. So the arrow will be here and here. That's what leads to structure B. And over here, this is X, that's Y, and that's Z. So the arrow is here and here. That's what leads to structure C. Over here, the arrow will be here and here. That's what leads to structure D. And so on and so forth. And so you can continue here and here. That will lead back to the original structure. So please, please practice how to draw your arrows. Again, I will insist on that. Practice how to draw your arrow. And I don't know, I remember I gave you guys the general scheme for drawing your arrow when you have a resonance structure. There are three types of resonance structure we've seen in this class. X equals Y minus Z, and you have a positive charge. When that's the case, the way you move your arrow is only one direction. That's the only way you move your arrow. And when you move your arrow that way, your resulting resonance structure is X minus Y equals Z, and the positive charge migrates to X. You have another case where X equals Y minus Z with a negative charge here, like the case we have above, like the case we have over here. In this case, the way you move your arrow is a little bit different from the first situation. Here, the arrow goes down, and then this one goes there. And so, your resonance structure will be X minus Y equals Z. Now, the X will end up with a negative charge. Then we have the third case, when X equals Y minus Z. Instead of having a negative charge, it has a lone pair without negative charge. In this case, the way you move your arrow is very similar to when you have a negative charge. So this goes here and this goes there. But now the difference here is that your resulting resonance structure, your Z will end up with a positive charge and your X will end up with a negative charge. Those are the three cases of resonance structure involving three atoms that we have seen in this class. And that's the way I want you guys to be able to move your arrow. So if I ask you to show your resonance, that's what I'm talking about. Does that make sense?
So in the example on this slide, you know how it has the electrons and the negative charge? Will we be moving the electrons or the charge?
You're moving the charge because what makes is the electrons that makes the charge in that case. Okay, and that corresponds to the situation I circled down there. It corresponds to the situation that you see circled over there. Does that make sense?
Yes.
So these are some examples of aromatic compounds. Okay, to satisfy yourself that these are aromatic compounds, you can do the cyclic test. you can do the plenarity test, you can do the conjugation test, and you can do the odd number of pair of double bond tests. If you do those tests on all these molecules, you will notice that they are all cyclic. So I will leave it for you guys to try it on your own and convince yourself that these are aromatic molecules by doing all those tests. Does that make sense? Anti-aromatic compound. So we've talked about aromatic and non-aromatic. So in terms of stability, aromatic compounds are very stable. Anti-aromatic compounds are non-stable. Okay, and so an anti-aromatic compound will fulfill the first criterion for aromaticity, but we have an even number of pi electrons. Does that make sense? So cyclic, planar, conjugation, and odd number. So for the anti-aromatic, instead of being odd number of electron, it will be an even number of electron. Does that make sense, guys? I want it to be clear. So the anti-aromatic, the only thing that will make it fail the test is that it will end up with an even number of electrons. And we've seen some example of anti-aromatic compound here. We've seen that some example in this molecule. Let me see in this class. Here, do you see that? CPCO. CPCO. It is cyclic, it is planar, it is conjugated, but it is not odd, it is rather even. Does that make sense? And so these guys will best qualify as being anti-aromatic. Okay, that's what I wanted you guys to see. Then non-aromatic, non-aromatic means you are neither anti-aromatic nor aromatic. Okay, neither anti-aromatic nor aromatic. So in this case, this guy here will be non-aromatic. And what makes it non-aromatic? You see that he has failed two tests, the CPCO. So it failed the C test and then failed the O test. So that's why it is non-aromatic. Does that make sense, guys? So in terms of CPC test, I will have my aromatic, I will have my anti-aromatic, I will have my non-aromatic. Okay, check, 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 check. You are aromatic. Check, 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 check. Oh, sorry. Check, and here you go even. Does that make sense? So with usually non-aromatic, I will say check. It will usually fail the plenarity test. The conjugation test, it will not really pass. If you are not planar, you cannot be able to make a full conjugation. So long as you already failed 2 out of the 4 criteria, you are non-aromatic. Does that make sense, guys? So long as you already failed 2 of the 4 criteria, you are non-aromatic. So is that a question or a hand raised?
A question.
Yes.
On the last, the chrysene, is that how you say it?
Say that again.
Chrysene,
Yes.
is that how you say it? Overall, it has 9, so it's odd number of pi bonds, right? So how did you get it to be even?
No. I am this table here.
Oh, it's a table separate. Okay.
So this table here is just for you guys to be able to distinguish between molecules that are aromatic, anti-aromatic, and non-aromatic. It has nothing to do with this structure.
Okay.
All of these structures here are aromatic. They are all aromatic.
Okay.
Yes, and I asked to prove it yourself. Okay, prove yourself that they are all aromatic by making sure that they all follow this rule. I left. Yes, I gave you that one as a small exercise for yourself. Okay, So you may also have some heterocyclic molecule. What we mean by heterocyclic molecule means that the molecule will have another atom other than carbon present in the ring. They will have another atom other than carbon present in the ring. We refer to them as heterocyclic. And then here the criteria for aromaticity is a little bit different. Their lone pair of electrons, for example, all of these guys are aromatic. Because if you notice, they all undergo the X, Y, and Z, and the Z here will be the lone pair. You see X, Y, and Z. The Z here is that lone pair. X, Y, and Z. The Z here is that lone pair. So the presence of that extra lone pair, although they are not sp2, this is not sp2, this is an sp3 oxygen. This is an sp3 nitrogen. So although they have sp3 atoms, they are still aromatic. Remember, the rule of plenarity only holds if you have carbons. All the carbons must be sp2. But if you have another atom, that other atom, because of the lone pair, it compensates for that rule. That's what I want you to pay attention to. Okay, so pyrrole, furan, and tyrosine are all aromatic compounds. And so you have more examples of aromatic compound. You have quinoline, you can convince yourself. You have indoles, you have imidazole, you have purines and pyrimidines. Those are all examples of aromatic compound, and these are very useful molecules. In your DNA, you have these guys. Those are the guys that are present in your DNA. When you be biochemistry, they will talk to you about purine bases and pyrimidine bases. It means we are talking about molecule made out of this guy and molecule made out of that guy. Those are all aromatic compounds. Okay, they are all aromatic compounds. Now, N. That's the end of chapter 8. Any question, guys? Okay, since you don't have a question, I have a question.
Actually, I do have a question. So on the slide, you had the stabilities and the cyclid with localized electrons are more stable than the anti-aromatic. Why is that?
Because the anti-aromatic, sometimes they will not even follow conjugation. Okay, sometimes they will not be fully conjugated.
Okay.
So let me create a poll here quickly, and then you guys can answer that question, and then we can move to A, B, C, D, and E. 30 more seconds. Okay. I guess my 7 people that are still sleeping are the ones remaining. You see that? Oh, somebody answered. They are back up. Okay. Mm, Okay, great. Thanks. You guys did a good job. Oh, sorry. Did I stop the polling? Oh, I stopped the polling without showing the result. Yes, all of you did a good job. Yes, Kay. I'm listening to you, Kay.
Sorry, it was an accident.
Or you just wanted to see how it works. So you guys did a good job. Most of you, if not all of you, selected E. Yes, the molecule must be cyclic. Yes, the molecule must be planar. Okay. Every atom must have p orbital. If you are planar, then you have a p orbital. Remember, sp2 means that you have an empty p orbital. Does that make sense? That's the meaning of sp2. Sp2, it means you have, because spp, that's the hybridization. If you use one s orbital and two p orbital, that's what called the sp2, and so you have an empty p standing. Same thing, spp. If you use an sp orbital, it means that you have two p orbitals standing. But if you have an sp3 orbitals, you don't have any p orbitals standing. Does that make sense? So C is correct. E is correct. And so the choice now would be, D is correct. And so the choice would be E. Does that make sense?
Hey, real quick, can we go back to an example?
To an example, like which example?
Just in a previous slide, so I can see like.
No, an example of determining aromatic and non-aromatic.
Yeah.
Let's see. That will be on chapter 8 slide. Oh, let's see. This slide, for example, you want us to go through this slide, for example, okay? CpCO. If I have to do that on that molecule, on the quinoline, the molecule is cyclic.
Yep.
All the carbon atoms, remember, I only emphasize on the carbon atom. All the carbon atoms here, if you look at all those carbon atoms, they are all sp2 carbon atoms.
Yep.
The system is conjugated. Double, single, double, single, double, single, double, single, double, single. You do see that. Now, in terms of number of odd electrons, pi electrons, I have 1, 2, 3, 4, 5. 5 is an odd number, so it passes the test. So that molecule is aromatic. And you can do that with the rest of the molecule.
All right, I got it. Appreciate it.
You're welcome, Tar. Chapter 18. Yes.
I'm sorry, my question was from that previous slide you were just on.
I knew that you would see it. I knew that. Let me imagine. It has to do with imidazole, right?
Yeah, I just wanted to clarify. You had mentioned that if there are two sets of paired electrons or there's another atom on there, you said that is what helps it be
It helps
aromatic.
in aromaticity, yes.
Okay.
And that's the case with imidazole, actually. Because this electron, you see, it wasn't, if you notice with imidazole, this lone pair of electron, we've decided to draw it inside the ring. There was a reason for doing it. It's because it contributes to the aromaticity. Same
Okay.
thing with the purine. If you look at the purine, you will see that this guy is drawn inside the ring. It contributes to the aromaticity. When it is drawn outside the ring, it means it does not contribute to aromaticity. So all the ones that are drawn outside the ring here, they don't contribute to aromaticity. Okay, so this one are drawn outside the ring. They don't contribute to aromaticity. This is outside the ring. It doesn't contribute to aromaticity. But the ones that are drawn inside the ring, they contribute to aromaticity. Does
Okay.
that make sense?
Yes, thank you.
You're welcome. Chapter 18, we're looking at the reactions of benzene. Chapter 8, the last slide of chapter 8 is actually the first slide of chapter 18. So that's why I decided to move straight to chapter 18. So we'll be looking at the reactions of benzene. And like I said, these molecules, we usually group them as a group 5 family, this kind of aromatic compound. Okay. The aromatic molecule, we group them in the big family. We call that the group 4 family. That's the big family in which we group them. And again, we've already discussed that benzene is an aromatic molecule. We all know why. Because benzene is cyclic, benzene is planar, it has a conjugation, and then it has an odd number of electrons. Does that make sense? And because it is an aromatic molecule, it is a stable molecule, and of course, it is aromatic. These are just the things that we've talked about earlier on. Okay. Now, and you see, these aromatic molecules are very important in nature. Okay. From the medicinal aspect, some of them are used in manufacturing drugs. For example, if you look at the antidepressant Lexapro, you will see that there's a benzene ring present in there. There's another benzene ring present over there. If you look at inhibitor of platelet aggregation, meaning making your blood, how do they say, dilute, helping to dilute your blood, you will always see those kind of aromatic molecule in there. Antihistamines for those who have allergy, you see you also have in those things out there. And for what we are fighting now today, this guy called COVID-19, I'm sure you guys have been hearing the word chloroquine all the time these days over the news. Chloroquine and hydrochloroquine, you notice that they are highly made up of aromatic molecules. So that's how important aromaticity can be. They really help us to be able to make useful compounds. Okay. Now, chloroquine and hydrochloroquine are originally anti-malaria molecules. And the difference is only the presence of this hydroxy group here. That's why this is called hydrochloroquine, because of the presence of the OH group over there, which is absent in chloroquine. Okay, so that's how that chloroquine molecule looks like. It is an aromatic compound. It contains a quinine or quinone, because this group here is a quinone group, which is an aromatic compound. If you go back to chapter 8 slide, you will notice that it is part of the groups that, guys, look, it's a quinoline. So that's the group present in chloroquine.
Dr. Zico,
Yes.
can you go back to the slide you were just on? Okay. Does the S on Plavix contribute to the aromaticity of
Does the what?
the S on Plavix, the drug Plavix? Does it contribute?
Yes,
Not
the S of the drug Plavix contributes to aromaticity, because look, that Plavix contains this structure here, thiophene. Do you see that?
yeah.
Yes, it contained thiophene, and remember, thiophene was an aromatic compound. So yes, yes, that S here contributes to aromaticity because you will have a lone pair inside and a lone pair outside. And remember, I said when you have lone pair inside, those lone pair contribute in aromaticity. Does that make sense?
Yeah.
So for those who want to go into the medical side of chemistry, it is called medicinal chemistry. This will be your job, trying to make molecules like this, molecules that will help in curing diseases. Those who do research with me, basically they will know it. That's what I do in the lab. I spend my time trying to make molecules that will cure some diseases. That's what those who do research with me spend time doing in the lab. Okay. Now, there are some other people that will be interested in other part of chemistry, in making commercial product. Again, you can make aspirin, which is salicylic acid. You know what aspirin is? Is the active ingredient in some of your under-the-counter drugs that you use regularly. And this is a bad molecule, right? You know why, right? You guys know this guy. It's a bad guy. It's a bad guy. That's what we call meth, methamphetamine. And in meth, you also have that our nice benzene ring present. You have an antidepressant, which is called amphetamine, which is a cousin to meth. You know, it is a cousin to meth. You can have artificial sugar, artificial sweeteners. Those who do industrial chemistry in companies, they use a lot of artificial sugars to make their product sweet, you know. And air freshener, what you use in refreshing yourself or your home, usually will contain that dichlorobenzene. So that's a little bit of versatility, how organic chemistry can be useful for pharmaceutical, for cosmetic industry, those who want to do makeups and all the like. That's basically the kind of stuff that are important for you guys to know. Those who want to do agriculture, in agriculture, some of them are used as fertilizers, some of them are used as toxins for these microbes that goes ahead and eat your crops, you know. You might use some of them. For example, you have over here this plane trying to water some of those organic molecules on the crops, probably to protect them for something. Some of them were also used for defoliation mission in the Vietnam War. So you can use them for good things and bad things, you know. It can be used for good things and bad things. Now, in terms of nomenclature, you can name benzene molecule, okay, monosubstituted benzene. The nomenclature is very easy. So monosubstituent benzene are named by adding the name of the substituent to benzene. For example, this is called bromobenzene because you have a bromine and a benzene ring. Chlorobenzene, nitrobenzene, ethyl because it's an ethyl group. Ethyl benzene, okay? Fairly straightforward without nomenclature. Same thing with this one. Some monobenzenes have names that are incorporated in the substituent. So it means that instead of calling this one methyl, because this can be called methyl benzene, we decided to call this one toluene. This guy is called phenol. This guy is called aniline, right? Kerlin Bell, aniline. You're familiar with that one, okay? This one is called benzene sulfonic acid. That's called benzyl sulfonic acid. That's its name. Trinity. I'm sure you're familiar with that structure. This is called anisole. This is called styrene. Those are common names. There's no logic why this is called styrene. Don't ask me how. You just need to know it that way. Because I don't know why your parents decided to give you your own name. So that's how they also decided to call this one benzaldehyde. That's why they decided to call this one benzoic acid. And that's how they decided to call this one benzonitrate. Does that make sense? So these are some of the common names that you will be required to know. I will not really say memorize them per se, but knowing them is good. Okay. In terms of substituent in the benzene ring, there are two types of substituent. You have the phenyl group, which is just a benzene ring. Usually I will abbreviate my phenyl group as PH. So henceforth, if you see me writing PH, you know that I'm talking about the phenyl group. And the phenyl group is made up of 6 carbons. Then you also have the benzyl group, which is made up of 7 carbons. So the difference between the benzyl and the phenyl is this extra CH2. And the benzyl group, people usually abbreviate it as BZ. You see it abbreviated as BZ. That's the benzyl group. Okay. And so if I want to name this guy, I will call it here. You can see this is the benzyl group here. The one I have circled, that's the benzyl group. So I can call it benzyl chloride. Does that make sense? It will be called benzyl chloride. Now, this other guy here, you notice that this is a phenyl group. Do you see that? And again, you can also circle it from this end. That's also the phenyl group. So that's why the molecule is called diphenyl. And it is an ether. Okay. With this molecule here, that's a benzyl group. Do you see the benzyl group there? And over here, you see another benzyl group. So that's why it's called dibenzyl. And it is an ether because it is breached by the oxygen. That's why it will be called dibenzyl ether, breached by that oxygen. Now, sometimes when you have alkyl substituent, okay, you can also name the alkyl substituent. Name as an alkyl substituted benzene when the alkyl has a name. Otherwise, name as a phenyl substituted alkane. So, for example, Over here, I have a 3 carbon, and so this will be called isopropyl benzene because this is the isopropyl group. It has a name. It has a name. Because it has a name, I will name it as isopropyl. Okay. This group here is a secondary butyl. It's a sec-butyl group. So I will call that sec-butyl benzene because it has a name. This is a third butyl group, so I will call that third butyl benzene. Now, when the substituent doesn't have a name, like this one, when it doesn't have a name, you will now name it as a phenyl substituted. So this will be called phenyl, so pH, 2-phenyl pentane. I will name it 2-phenyl pentane. And this other one will be called 3-phenyl pentane. Question? Any question before we close? So those who have a lab with me tonight, we're meeting at 2 o'clock. It will not be a long lab. We'll basically just go through the new syllabus and I will tell you the expectation for the rest of the semester. That's basically what we have to do at 2 o'clock. So let's meet at 2 o'clock and then do the discussion. Any question? If you don't have any question, then I will say this will be the end of our class for today. And see you guys on Thursday to continue with chapter 18. The homework is open. And I notice that most of you don't do the homework. Please, guys, do the homework. Do it. It's important. And your exam will most likely be using Mastering Chemistry. You'll be using your homework platform for your exam. So I will create an exam on the homework platform. That's where your exam will be. So do your homework will also help you practice for the exam. Okay, if we don't have any question, I will dismiss you guys. Thank you for being around.
Thank you,
Hey,
Dr. Rico.
Jaquira. Yes.